Today's lecture, Chapter 8, will be broken into some smaller parts, but we'll start off with talking about metabolism. So metabolism is the reason that our cells can run all these small chemical reactions. In fact, a living cell is a miniature chemical factory, and chemical reactions are occurring all the time. The cell has to extract energy from the molecules that have energy stored in them, and then that energy is then converted into useful energy that can perform cellular work. Some organisms, such as fireflies, convert chemical energy into light, those lovely little glowing green things that you see in the summer, especially up north. So the important definitions are firstly metabolism, and metabolism is kind of like the umbrella, and it includes both anabolism and catabolism. So metabolism is the sum total of all of the chemical reactions happening in a cell. Anabolism is where you're actually consuming energy and you're building complex molecules from simpler ones. So an example of that would be photosynthesis or protein synthesis. And those are where you're making larger complex molecules from simple ones, from your monomers. Catabolism is the energy pathways where you actually are breaking down complex molecules and turning them into simpler ones. And these complex molecules can become the building blocks for your anabolic reactions. So the breakdown of catabolic products becomes your starting molecules for anabolic pathways. So in a cell, our pathways are all organized, highly organized. And so we all start with a specific molecule, which is what we would call the substrate. And so in this example here, the starting molecule is substrate A. And then each step along the way is catalyzed by an enzyme. So in order to make A into B, we need enzyme 1. And once we have product B, it becomes starting molecule for reaction 2. And we're going to make product C using enzyme 2. And when they go from C to D, we use enzyme number 3. Without these enzymes, these reactions would not proceed. And so you end up with your product D, but you had to go through a number of steps in order to get your product. And this is what's constantly happening in our cells. And we will learn in this chapter about these molecules called enzymes and how without enzymes, nothing can happen in a cell. So the best example of a catabolic pathway, which we'll go over and over again, is cellular respiration. So what is cellular respiration? Cellular respiration is where we take a molecule of glucose let's just put that where we can find it. We take some glucose, add some oxygen, glucose plus oxygen, glucose from the food you eat, oxygen from the air that we breathe, and we turn that into, we break that down into carbon dioxide plus water, the products that you breathe out, and energy. And the energy that a cell can use is known as ATP. So we've heard of this word before. By the end of this chapter, we should have a much better understanding of what ATP is. So ATP is the energy storing molecule that cells need to run. It's the currency that cells run off. The example of an anabolic reaction is going to be our photosynthesis, or synthesis of proteins from the monomer amino acid is a great example of anabolism. So when we talk about bioenergetics, it's how do organisms manage their energy sources. So there's different forms of energy. Energy has the capacity to cause change. We've all seen the powerful energy that tornadoes have when they whip through whole cities and blow them up. Energy exists in various forms, and the two main forms of energy that we're concerned about are number one, potential energy, and number two, kinetic energy. Potential energy is the energy due to your location or to your structure. So location, where you are, if you're at the top of a table, you've got more potential energy than if you're standing at the floor. Think of that wobbling effect that you might feel when you're on the top of a ladder. You've got a lot of potential energy because you can be attracted to the ground by gravity. Or your potential energy due to your structure. Think of glucose. Think of all the food you eat. The food has all got stored potential energy that we're going to extract in order to make energy, useful energy for the cell. And then kinetic energy is energy due to its movement. So when our muscles are actually powering our movement, they're actually taking stored potential energy and converting it into kinetic energy, energy of movement. So that becomes the next big topic. Energy can be converted from one form to another. So when we look at this picture here, you can see examples of potential energy. The top of the diving board, you've got a lot more energy than when you've come into the water. As you go in from the top of the diving board into the water, you're changing your potential energy into kinetic energy, and you've got very little energy when you're back in the water. You've got less potential energy than up here, and you've actually, in order to get back to the top of the diving board, you will have to convert some of your stored energy into the energy of movement or kinetic energy so that you can start this cycle again. And so with these talks of energy, there's two laws you need to understand. The first law of thermodynamics, and that law is energy cannot be transferred. No, energy, I always say it backwards. Energy cannot be created or destroyed. It can only be transferred or transformed. That all the energy in the universe is constant. It's just in changing forms from one form to another. And here's your first law of thermodynamics in terms of the bear eating the fish. The fish has chemical energy, stored chemical energy, and when that bear eats that fish, he changes it into a form of energy that he can use in order to operate. The second law of thermodynamics is where energy transformation increases the entropy of the universe. And what is entropy? Entropy is disorder, and a disorder is kind of like, I like to think of it as messy. Things that are messy are disordered. And so if you don't put energy into something, things get really messy. Now, it's actually interesting when you look at this picture over here, you're seeing that the energy that this bear got from eating that fish has been used to power his cells and do cellular respiration. And so he's giving off carbon dioxide and water, but also some of that energy transfer is being lost to the environment as heat. And that heat is basically increasing the disorder of the universe at such a minute amount that you wouldn't know the effect. But that's why the energy exchange is not 100%. And that's why even biological systems, increasing the disorder of the universe is still a valid statement. For the most time, when we talk about biological order and disorder, cells are constantly creating order from disorder. Think of your drawing of a cell and how we drew all those little organelles in it, but those organelles were actually made up from your macromolecules. And so when your macromolecules, we had them in our body because those molecules were made from those smaller molecules, the monomers of them, and each of those monomers were made by using chemical energy in order to make those larger molecules. And ultimately, all the energy that we use for biological life came from photosynthesis, from energy from the sun, and then that is transformed into chemical energy that we can use to run all our reactions. So biological cells have incredible order, but we are contributing to the disorder of the universe because at each step some of this energy is lost.